Hello everyone, we are Group 18 and we are happy to present you a 3-motor tilt-rotor VTOL that have been designed as a final project for the MEC 491 Mechanical Engineering Design within the Koç University. Our advisor is Metin Muradoğlu. What is a 3-motor VTOL UAV configuration? We have combined a quadrocopter advantages such as the safe takeoff and landing, as well as aerodynamics efficiency for the traditional planes in the hovering mode. So it's a hybrid design. Our propulsion consists of 2 front motors tilt-rotor configuration, and our current specifications are 2 meters wingspan, 3.4 kilograms mass, and with 15 minutes of cruising speed. Our mission is optimized for surveillance with a vertical takeoff and efficient cruise. Our capabilities are the full cycle for the vertical takeoff to data collection and vertical landing. So here you can see our finished prototype within the lab of KU AVA within the Koç University. Our goals are the stable and controlled flight, which we have achieved, 20 minutes of endurance, which was partially achieved. We have achieved a 5-minute flight with the battery usage of only 13%, which implies the capability to fly even more than 20 minutes. Total mass below 4 kilograms, which we ended up being 3.4. However, on horizontal transition, we have achieved it, and it being fully complete within 1.2 seconds. And autonomous dynamics, we did achieve it through the companion computer using a mission-based and environment-based control flow demonstrated. Here is our initial design done on the Xaflor 5. Here you can see the plots of it. Our aerodynamic design validations, our aspect ratio is quite on point, while the static margins is quite high, but at the same time, it provides a more steady flight, even though less maneuverability. Our propulsion and power systems, we're not going to go through everything, but mainly we are using 3 motors, F90T motors, as well as the Blaze 7043 type Blaze propellers on them that are all getting powered by the 6S 5000 mAh LiPo battery. Our current thrust to weight ratio is approximately 1.8 to 1, allowing us for a vertical takeoff and controlled hovering. And our cruising requires only 1.2 thrust per motor, which is required during the flowing of the 1.2 kilogram thrust, which is less than 40% of the current motor's capabilities. Our structural design, we have used multiple different types of the carbon fiber reinforcements, 3D printing filaments and components, manufacturing machines and structural validity. Everything was used with the respect of their advantages from the engineering perspective in order for allow us to cut as much weight as possible and still obtain a safe and structural integrity within the plane itself. The tilt-rotor mechanism, the MATLAB torque code was developed in order to calculate the minimum needed torque, which ended up being 0.38 newtons meter. So we've decided to use a 10 kilogram per centimeter servo, which does provide us of 2.5 safety factor. Here you can see a schematics of the plane, initial schematics of the fuselage. The main wing. We have developed the internal ribs fully customly created, which did allow us to run a more advanced ANSYS structural test on it, because the 3D printing files itself do not allow you to run a proper validated results, but through creating a custom infill system, your results from ANSYS structural are way more confirmed rather than the previous option. Here you can see that we have obtained a mass reduction by 30% and 20% increase in stiffness. Here you can see example of our model. Now regarding ANSYS analysis, here you can see the example of forces applied and the mesh. All of this was done at a cruising speed 15 meters per second. As you can see, our total deformation and elastic strains are within the allowed levels of the materials used. Since we have confirmed that we are in the safe range, we can confirm that our structural stability and integrity is quite well designed. Now regarding the ANSYS fluent, which was done through the Ahmed Bari inspired approach, has shown that our LC and CD, CL and CD values are quite coherent with Xaflor 5 values. You can also see the velocity magnitude and the static pressure magnitudes, since you can see the differences between the top of the wing and the bottom of the wing. We can confirm that the lift will be generated. System architecture, we're not going to go deep into this, but here are the all components that we have used and all the powering systems. Here is the whole wiring schematics and the whole protocols that are running on time live on the plane. Regarding the simulation, you can see here how the gazebo simulation is running. The Q ground is also showing the mission, and we have live update on the streams. Now, regarding the future improvements, we believe that wing reinforcement could be way better approached. The CG and CP values could be way better designed. The tilt servo, there has to be a huge changes in the mechanism of tilting. The wing internal structure could be also optimized and would allow us to obtain even less reduction in the mass. The surface finishing, which could be a future epoxy finishing, is also quite interesting. Motor selection, we believe that there is plenty other options that can be used for this work, and as well as a mass optimization, which is also would be quite possible within the scope of the future work. So here is our references, and thank you so much.